In today's discussion, we are going to see what a derogatory and a non-derogatory matrix means. Now, before I go to discuss what a derogatory and non-derogatory matrix is, we first need to understand two very important concepts called as a monic polynomial and a minimal polynomial. Now, we have already seen the concept of finding the characteristic equation for a given matrix A. So, I have written the characteristic equation for the matrix A over here. Now the left hand side of this equation, which is contained lambda cube minus 5 lambda square plus 8 lambda minus 4. This left hand side of the characteristic equation is called as a polynomial. Poly means many and nomial means terms. So this left hand side contains many terms, hence it's a polynomial. But have you noticed that this polynomial has lambda cube, the highest powered variable, and the coefficient of this lambda cube is 1. Over here also, if I take the other example, the left hand side is a polynomial, and again I observe that the coefficient of lambda cube, the highest powered variable, is 1. So whenever you have a polynomial where the highest powered variable has coefficient equal to 1, the polynomial will be called as a monic polynomial. Now let's come to the next concept called as a minimal polynomial. So a minimal polynomial is basically a monic polynomial. You know what a monic polynomial is? Coefficient of the highest powered variable should be equal to 1. A monic polynomial of lowest possible degree. Here the degree is 3, or there also the degree is 3. So monic polynomial of lowest possible degree which can annihilate any given matrix A. Now listen to this word very carefully. The word annihilation, annihilates, simply means destroy or destruction. So if you are able to find a monic polynomial which is of a lower possible degree such that it can destroy matrix A. Now what do you mean by destruction of matrix A? We will come to that concept in a little while from now. So you simply remember the definition. It says a monic polynomial, lowest possible degree, such that it can destroy, it can annihilate matrix A. Then that monic polynomial is called as a minimal polynomial. So I'm going to take two examples here. This example, I have taken a matrix A, I have got the characteristic equation. So I'm going to find the roots of this characteristic equation by using synthetic division. The coefficient of lambda cube is 1, lambda square is minus 5, lambda is 8, and the constant is minus 4. So write the coefficients. Assume that the root of this equation is going to be 1. So I've taken 1 over here, bring 1 down as it is. 1 multiplies with 1, you get 1. Minus 5 plus 1 is minus 4. 1 into minus 4 is again minus 4. 8 minus 4 is again 4. So 1 into 4 becomes plus 4. The answer is coming 0 over here. So whenever you get the remainder as 0, be very sure that the value that you have taken is a root of the equation. So 1 is the root. So if one of the root is 1, then its factor is lambda minus 1. See, root is 1, factor becomes lambda minus 1. The other factor is simply obtained from the remainders which are over here. There is 4, which will become the constant. There is minus 4, it will be accompanied with lambda, and then there is 1, it will come with lambda square. So that's lambda square minus 4 lambda and plus 4. That's a quadratic equation, and you can very well observe that it can be factorized as lambda minus 2 the whole square. So now I can observe that this characteristic equation has given me the eigenvalues 1, 2 and 2. The eigenvalues are repeating over here. We also know that from the Cayley-Hamilton theorem, the given matrix A is definitely going to satisfy its characteristic equation. So what I have done here is lambda has been simply replaced with A. So I am writing A cube minus 5A square plus 8A and minus 4I equal to 0. Now we have already seen what Cayley-Hamilton theorem says. It says that every square matrix A will definitely satisfy its characteristic equation. That means if you try to solve the left hand side of this equation, it is definitely going to come equal to 0. Now here comes the concept of minimal polynomial. If you take these factors lambda minus 1 and lambda minus 2, now observe this carefully. I can construct two different equations from here of a possible degree which is less than 3. take 1, take the other factor as 2. So that's lambda minus 1 and lambda minus 2. So lambda minus 1 and lambda minus 2 and multiplied will give us the equation a square. See, lambda square minus 2 lambda minus lambda and plus 2. So that will give us the equation a square minus 3a plus 2y. Lambda square minus 2 lambda minus lambda becomes minus 3 lambda, minus 1 and minus 1 becomes plus 2. So that's plus 2i over here minus 3a square. Now people, if you try and solve this equation a square minus 3a plus 2y, it is definitely going to come equal to 0. You can use your calculators. You have matrix A. You have this equation a square minus 3a plus 2y equal to 0. You can try out this on your calculators and you will definitely observe that the answer is going to come 0. Let's take the other possibility. If I take lambda minus 2 and lambda minus 2. Now lambda minus 2 and lambda minus 2 is going to give me lambda square minus 4 lambda plus 4, which when written in the matrix form will give us a square minus 4a plus 4i. Now people, as I said again, you have the calculators. Use the calculator to get a square minus 4a plus 4i. This time you will not get the answer as 0. That means this polynomial, our polynomial a cube minus 5a square plus 8a minus 4i equals 0. This polynomial is definitely going to give us the answer 0, but it can be reduced to a polynomial of degree 2. See, the polynomial has reduced to a lower power, degree 2, such that the answer is still coming equal to 0 and I will still use the same factors 1, 2 and 2. But the other two factors 2 and 2 is not giving me the answer 0. This equation has been obtained from the other two factors 2 and 2. This has not given me equal to 0. But a square minus 3a plus 2y is definitely going to give me the answer equal to 0. And the power of this equation is also less than 3. Then this particular matrix, this particular equation is destroying matrix A. The answer is coming 0. That is what we call destruction. So this equation is called as a minimal polynomial. Similarly, if I take the other case, this particular matrix where the eigenvalues are not repeating, I've got my equation a cube minus 2a square minus 5a plus 6i equal to 0, again from the Cayley-Hamilton theorem. This time if you observe, there are 3 distinct eigenvalues. So I can form 3 different equations for equation whose power is less than 3. I can take 1 and 3, I can take 3 and minus 2, I can take 1 and minus 2. 1, 3, 3 minus 2, 1 minus 2. These pairs will give me 3 different equations. A square minus 4a plus 3i, a square minus a minus 6i, a square plus a minus 2i. I have simply multiplied these 3 values, taken 2 at a time. Take 1 and 3, take 3 and minus 2, take 1 and minus 2. I've got 3 equations. And people, you again have matrix A. You can definitely get the answers for these 3 equations. And this time the answer is not going to come equal to 0. That means only the first equation, a cube minus 2a square minus 5a plus 6i, this is going to come equal to 0, but not the equations which contains a square. That means these equations are not destroying matrix A. Hence, these equations are not the minimal polynomials. So basically, a minimal polynomial is nothing but if you have an equation, a Cayley-Hamilton theorem equation, which can be reduced to a lower power such that the answer is still coming equal to 0, then that particular polynomial is called as a minimal polynomial. So I'll give a very shortcut technique to remember what a derogatory and a non-derogatory matrix is. So over here, the eigenvalues were repeating. Eigenvalues got repeated. The matrix, the Cayley-Hamilton theorem equation has reduced to a lower power such that the answer is still equal to 0. Such matrix is called as a derogatory matrix. If you are not able to find a minimal equation, such matrix is called as a non-derogatory matrix. The power has not reduced. That means this particular matrix is a non-derogatory matrix. So here comes the shortcut technique. If the eigenvalues of a matrix are distinct, if the eigenvalues of the given matrix are distinct, the matrix is definitely non-derogatory matrix. And if the eigenvalues of a given matrix are going to repeat, then the particular matrix is a derogatory matrix. Here the eigenvalues 1, 2 and 2. 2 has repeated. That means the particular matrix is going to be a derogatory matrix. Here the eigenvalues are distinct. Hence the particular matrix is a non-derogatory matrix. So people, this is what the concept of derogatory and non-derogatory matrix is. Revise it very carefully. Thank you.